So previously we used the Maya-Vittori sequence to calculate the homology of spheres. And now we're going to start doing some various other kind of examples of things that we can calculate with the Maya-Vittori sequence. First, we'll just have a kind of general lemma. Let's suppose that X is the union of two open sets, as in the usual deal with the Maya-Vittori sequence. And I'm going to suppose that U intersect V is contractible, and that U and V are path connected. Each of them individually is path connected. Then I want to claim that well, H0x is just going to be the integers, because X is going to be path connected, and then HIX is going to be HI of U, direct sum HI of V. That's for all strictly positive I. So proof falls. So we're going to use the truncated Maya-Vittori sequence. Okay, so remember that we proved that if you can use the ordinary Maya-Vittori sequence, but in the case where U intersect V is contractible, or where U intersect V is connected, which of course is a consequence of being contractible, then you can modify the Maya-Vittori sequence by just replacing all the H zeros with the zero group. So what do we get? We get HI plus 1 of the so we get HI of let's write it this way. So we get HI of U, direct sum HI of V. That goes to HI of X. That's the one that we're mostly interested in. And then coming in, you've got your HI of U intersect V. And then you've got your HI minus 1 of U intersect V over here. And so this is going to work for I bigger than 1, and then for the case I equals 1, so because we're using the truncated version, well, this H0 would actually be Z, but because we're doing the truncated version, all the H0s get replaced by Z. But U intersect V was contractible, and so it's got the homology groups. So all the homology groups above the dimension 0 are just trivial. So this HI is 0, and this HI is also 0. And then because here we're saying I is bigger than I bigger than 1, so I minus 1 is still bigger than 0. So that's 0. So in all cases, all of these cases, we're seeing that HIU plus HIV goes to HIX. So in all of these cases, we've got this map here with zeros on either end, and so by exactness, that forces it to be an isomorphism. And if you go back to the place where we proved, we set up the truncated thing, we discussed what happens with H0, and in this kind of case, when U, V, and U intersect V are all connected, then X itself is also connected. So in this case, we see that H0X is just going to be equal to Z. Okay, so now we can prove an interesting theorem about the homology of certain group class spaces. Okay, so let's suppose simplicity that n's at least 2. Let's say W. Let's call it U maybe. U is a convex open subset of R of the n. And then we've got some distinct points A1 up to AM in U. Okay, so we're going to consider the complement. So we take this convex open set and we're going to remove m points from it. Okay. The main case that we're actually interested in is where U is the whole space Rn. Right? So here we're looking at Rn and we remove some finite number of points. That's a fairly natural space to consider. And want to know what's the homology of that. Okay, so I want to claim the homology is like this. You get to, well, this is going to be a connected space. So in dimension 0, you just get a z. Then you'll get m copies of z in dimension n minus 1, and everything else is 0. So the proof's going to be by induction on the number of points that we remove. So m is 0, then the space we're looking at and the space x is just equal to u in that case. So that's a convex set, so it's just contractible. So the homology of x is just a single copy of z in degree 0. Okay, that's easy enough. What about when m is equal to 1? Okay, so you take a convex open set and you remove A1. Okay. Okay, so we're going to choose some epsilon. Okay, so use an open set, and A1 is supposed to be an element of U, so we can choose some open ball around it. Okay, so then I can define some I, say, from Sn minus 1 to U with A1 removed. I of some vector x is going to be A1 plus epsilon over 2x. And now it's not hard. We've seen stuff like this before. This is going to be fairly easy to see that this is a homotopy equivalence. And so the homology of our x in this case is the same thing as the homology of Sn minus 1, which is how it's supposed to be. So the m equals 1 case is basically just the calculation homology of spheres, as we've seen previously. Okay, so let's now suppose that m is bigger than 1. Okay, so I would choose so we've got, let's look at all these vectors ai minus aj. There's only finitely many of those. So we can choose a unit vector that's not perpendicular to any of these ai minus aj's. So the point about that is, if we look at the dot products, these are all different, right? So if two of them were the same, if a dot ai, u dot ai is the same as u dot aj, then that would mean that u is perpendicular to ai minus aj. Okay, so it doesn't matter in what order we listed these points, so we might as well renumber them so that these things are in order, and that would be convenient. Okay, so let's maybe have a little picture here. This is going to be my u, my a1, a2, a3, a4, say, and and then if I take my unit vector u to be kind of like this, so that the dot products with u increase along here. Okay, so the point about having this vector is that I can use it to kind of screen off part of the set. I'm going to draw some lines here that are perpendicular. These are going to be lines perpendicular to u, or in the higher dimensional case, these will be hyperplanes of dimension n-1 that are perpendicular, like so. So we're going to choose P and Q, say u dot a m-1 less than P less than Q less than u dot a m. So this is going to be where u dot x equals P. This is going to be the plane where u dot x is Q, and that fits between A3 and A4 as indicated. Okay, so so then we're going to let V be so V is everything kind of below this the second line, and W is the stuff above P. Okay, so so your V is kind of down like that, and your W is everything above here. So these are both convex open sets still, and U is V union W. Okay, so for you, we've got X is U with all these guys removed, and then we've got our V and our W like this, and so then we're going to put Y is X intersect V. Okay, so so V is the stuff down here, so that's the same thing as taking V and removing all the relevant points that lie in V, which is A1 up to AM minus 1. And we're going to put Z is X intersect W, which is So that's everything that's going on kind of up and to the right of the second line. So here we're just taking W and removing AM. Okay, so and we're working by induction. So remember, V and W, these are both convex open sets, so the induction hypothesis is applicable to these. So by the induction hypothesis, we know that H star Y is, you've got a Z in dimension 0 and then a Z to the n minus 1. And then 0's passed there. And similarly, the homology of this Z. Okay, so this is just the case m equals the kind of m equals 1 case. Take a convex open set and remove a single point. Yeah. So that was sort of supposed to be for the case two-dimensional case. So here we should say this is happening here in degree n minus 1. Okay, and then for your Z, similarly, you've got a 0 here in degree 0, and then a single Z up here in degree n minus 1, and then everything else is 0. Okay. Okay, so that's the homology of Y and Z, and Y and Z are open in X. And X is the union of those, and Y intersects Z, so that's just the set of X in U with little u dot X between P and Q. Okay, and there's no points to remove in this band, right? We put these two lines kind of between the AM minus 1 and the AM. There's no points to remove. So we've just simply got a convex open set. So this is contractible, okay? So the previous lemma gives so H naught of X is Z, and HI of X is HIY plus HIZ when I is bigger than 0. And so looking here in n minus 1 group, you get the Z to the m minus 1, and that Z is Z to the m. The other groups are 0. Okay, so that completes our induction step, and it tells us what we get if we what we get for the homology if we start with a convex open set and remove some finite list of points. Okay, so that's our first example of the Maya-Vietoris sequence, and then the next couple of videos we'll do various other examples.